Assalamualaikum and a very good evening everyone. So basically today we're going to continue on where we have left. Basically today we're going to finish off this chapter. There are a few things that we need to cover by today. First we're going to look at on the write cycle of 68K to the external peripheral. So basically I'm going to cover the main important things that needed to be covered today is all for you to understand on this what happened during the read and write cycle on 68K to the external memory or peripheral. So before that, let's recap on what we have learned so far. So last Tuesday, if not mistaken, we have covered on the type of pins that are available in a 68K microprocessor, and we have looked at what category of pins that are available, what type of pins that is and its purpose, and then we have looked at what are what we call this as essential system support pins for 68K, reset, what is halt, and the buses on 68K. Basically we have the address bus and we have the data register bus and such. Okay, so today we're going to look at a little bit on the operation of interfacing 68K with a peripheral. Specifically, we're going to look at how does the process being done, what is happening during the write cycle and what is happening during the read cycle of 68K to the external memory or to the external peripheral. So basically we can represent the process by using what we call as this timing diagram. Okay, and timing diagram is basically a diagram to denote the timing for each of the pins at the 68K. We have your clock pins. Okay, basically your clock pins, its purpose is to connect your 68K to a clock which generate pulses, a train of pulses, and then A1 to A23 is denoted by the address bus, and then we have the read and write pin, and we have your AS pin. If you remember, AS stands for what we call as address select, if I'm not mistaken, or AS is, wait a minute, AS is what we call as address select pin, if I'm not mistaken. And then we have the UDS, upper data stroke and lower data stroke pins, detect, which is an acknowledge pin, your buses D0 to D15, and then finally is the functional support pin, FC0 to FC2. Okay, so let's look at what happened during the write cycle. So during the write cycle, basically the timing diagram look like this. Okay, initially if you not familiar with this, maybe it's hard for you to see. The description is written at the left side of the slide and the timing diagram is shown at the right side of the slide. So it's easier for you to see based on the states at particular time in the diagram, in the timing diagrams. For example, S0, if you see this clock over here, okay, S0 state is, this denote the states during the S0 part. So it's easier for us to understand if we follow states by states. Okay, let's look at what happens at the first state. Okay, so during the first state, what happens is that first, okay, based on the description written here, the 68K, okay, remember the 68K will put a function code FC0 to FC2. So this FC0, FC2 just now is the functional support pins to denote the status of the 68K, okay. And then we go to state number 1. So what happened to state number 1? Okay, this state. Probably use this color. Okay, next one. Okay, it will start from here actually. State number 1. So during this state, okay, during this state, what happens is that your 68K will put out the number, actually the number in bits in address bus A1 to A23. If you can see here, if you see A1 to A23 will change its state. Okay, so meaning that during this clock cycle, or during this state, your 68K will put whatever address value that it is currently addressing. So that is what happening during this state. Okay, and if you can see, there's no other changes in the other pin. And then we're going to the next state. So number 3, what happened during this state is that after putting the addresses on the addresses bus, the 68K will pull your address select and your read write to 0. So we are currently in this state. Okay, so address select and read write will be put to 0. So that is what happened during the second state. Okay, and then we're going to next to the third state. So during this state, what will be happening? See, what will be happening? So particularly there's no change actually, but if you can see during this state, the 68K, what your 68K will do is they're gonna put the data that belongs in the address onto the address bus. So you can see here there's a change of state in this data bus. Okay, data bus. So that's what happened during the third state. And final state for the first 68K cycle here. So what will be happening here, if you can see, your upper data stroke and lower data stroke will be put to low. Okay, will be put to low. So after this first part is executed, meaning that the 68K, you can imagine that this 68K is connected to external peripheral. Okay, there's an external peripheral, and the bus, the address bus, the data bus, the UDS and LDS, everything is connected between the peripheral and 68K. So at the first part of the write cycle, after the 68K have put both the UDS and LDS to 0, okay, meaning that you can think of it like it's already telling the external peripheral it already sent all the data to the buses, to the correct bus. So now it's up to the task of peripheral to take the data and put it inside its memory or something like that. Okay, so now we go to the peripheral part. Okay, so what happened during the this fault state actually is still in the fault state. Once the UDS and LDS has been put to 0, the peripheral will acknowledge that the data has already been sent at the address and data bus. So what it does is first is going to decode the address. So let me screen for this. First it's going to decode the address that is being put on the address bus. Okay. So once it's identified which address is being sent by the 68K, it will allocate that address inside this memory, and then what it does inside this address, it will take the data that have already been sent by the 68K. So you can imagine it like this, yeah. First, 68K will tell the peripheral, okay, you need to put data at this address, and then what the peripheral does, it will identify the address inside of its memory, and then it will take the data from the data bus, put it in the address that being sent by the 68K here. Okay. So this process will happen at a few clock cycles. If you can see, at state 5 and state 6, there's no change of states in any of the pins. But if you can continue, after state 5 and state 6 has passed, you can see that the 68K, generally, because we are using the words, for example, words, we are sending word size of data, it will take 2 clock cycles. So after 2 clock cycles, what the 68K will do, okay, after state 5 and state 6, which is 2 clock cycle, what the 68K will do, it will put the UDS and LDS to 1 again. Okay, you can see UDS and LDS to 1, and then it will deactivate the data. See, part here. Okay, part here, the data will be deactivated, and AS will be deactivated as well. Okay, and then finally it will put the read and write, this part. Okay, this part is after S7 to 1. Okay, and then lastly, after you put the read to 1, the peripheral, your peripheral will assert detect 1 to 1 back. Okay, your peripheral will set the connection to 1. So detect here, if you can see back, the detect here is just for the peripheral to acknowledge that it has done its job. Okay, it has done putting the memory, and then the 68K will reset back all of the UDS, LDS, AAS, and read to the original state, and then the peripheral will acknowledge that. So that is the end of the one write cycle. So on every write cycle, you can imagine this will happen between your 68K and your external peripheral. So this will go to the next cycle. So depending on how many bytes you are sending to the peripheral, so this cycle will continue until all of the data has been sent from the 68K to your peripheral. Okay, that is on the write cycle. And then let's look at what happened during the read cycle. Okay, the read cycle. So basically, read cycle is for your 68K to read from the peripheral or to read from the external device. So what happened during this cycle? Okay, so first we start at S0. We're going to start as S0 again. So let me just now is black. Okay, start as S0. This is the initial condition. Okay, now the 68K want to initiate a read cycle. So what does it do? Okay, first, again, it will put out the status of the microprocessor. Okay, the FC functional support pin FC0 to FC2 is just to represent the status of the 68K, and then on the next cycle, okay, this is on the initial part. Okay, now we're going to the next cycle. On the next cycle, what it do, it will put out the address. So the 68K will put out the address onto the address bus. So this is the address bus. So you imagine if your 68K is currently trying to access a certain address, it will put out on the address bus. Address bus is basically again is a collection of pins. Okay, so it'll put out the address denoted by the number of bits onto the address bus. Okay, so now your address bus is from nothing, from high impedance state to becoming state represented by number of bits that the 68K is trying to address. So this is when the S1 cycle. Yeah. So then what happens that, so during this state, you put the address on the address bus, and then what you do is that to tell that it is currently trying to access external peripheral to get a data from the external peripheral, what you do, it will put the AS and LDS to 0. Okay, on this part here. Okay, so this part. One more thing I forgot to mention, okay, it's not written over this slide. Before that, at the previous state, apart from putting the address on the address bus, your read-write will be turned to 1. Okay, your read-write will be turned to 1. Okay, then followed by the putting the AS pin and UDS LDS pin to 0 on state number 2 here. Okay, state number 2 here. So once that finish, it's already understood by the peripheral. The 68K is currently trying to access its data. So now it will go to the peripheral part. Okay, peripheral part. So what will the external device or peripheral will do during this particular time? So because now you already knew that the 68K is trying to access its data. Okay, so you have your, again, for you to see it clearly, you have to imagine that currently your 68K is connected to your external memory. So I denote this by M via all of this bus here. Okay, all of this bus and all of this pin. So after this have completed, after this part have completed, now goes to this part over here. So during this part, what will happen is that the peripheral already knows that the 68K is trying to access its memory. So what you do first, you need to decode whatever address that is being put on this address bus by the 68K. So this goes in state number 3. Okay, state number 3. Okay, decode address. So this goes to point number 3. And then what it'll do, it will first, this is actually in reverse, but never mind. What it'll do, first it will actually pull, okay, this takes it 2 cycle, 2 cycle over here, and then what it'll do, it will pull your detect to 0, meaning that it will acknowledge that, it will tell the 68K or acknowledge the 68K that it will acknowledge that 68K is trying to access its data. So it will pull the detect to 0, and then at the same time it will put whatever data from the memory to the data bus. Okay, so this is over here. So if you can see, whatever data that is contained inside the external peripheral is now being put over the data bus D0 to D15. So this part here. Okay, so depending on the size of the data, normally it is in word or byte size. So if it's word, it will take 2 cycles to complete, and then we're going to go to the next cycle. Okay, once this is detect is acknowledged and data is already being put on the data bus, we'll go back to the 68K, see that what will the 68K do. Okay, so first the 68K, once state number 5 and state number 6 is executed, your 68K, okay, this back to 68K, so I use red color. So the 68K will take the data and go inside and will retrieve the data from the data bus and will put it inside its memory. Okay, so this is in 68K lah. 68K. Okay, we'll put inside the memory. So once you do that, once the retrieving of memory is completed, what the 68K will do, it will reset back the UDS and LDS, okay, to 1. So this part here, and there it will deactivate AS to 1. Okay, so this part, this boot part. Okay, so that's what happened. So once it put the UDS and LDS to 1 and deactivate AS back to 1, the peripheral, your external peripheral or your external memory or whatever, will acknowledge that. It will reset back the data on the database to 0, to high impedance state, and then it will activate deactivate detect to acknowledge that the cycle is completed. The read cycle has been completed. So that is how your 68K perform a read and write cycle to the external memory or to external peripheral. So that's about it. Okay, so just to recap, this is the cycle for the write process. 68K, put the data on the address bus, activate AS and RW, activate UDS and LDS, and then the peripheral will decode the address that was sent by the 68K, take out the data, and then it will acknowledge and detect, and goes back to the stop transfer part, okay, where the 68K deactivate ULDS and LDS, deactivate AS, reset back the data, and put RW read write pins to 1, and then the peripheral will acknowledge it. So this goes the same, roughly the same process with the read cycle. Okay, So that's about it on the read and write cycle for 68K towards your external memory or the external peripheral. Next we're going to look at special purpose pin on the 68K. Okay, so what are the special purpose pin in a 68K? So first, it provide function not needed in basic system. Okay, this is a special purpose pin. Okay, basically this is not being covered before because in the basic system this is not crucial for the basic operation of 68K. So what are they? What are the special purpose pin? Can be divided into 5 groups. We have the bus error control, we have the function code output, the interrupt control pin, bus arbitration control, and lastly we have the peripheral control pins. Okay, special purpose pin. Okay, special purpose pin. First, let's look at what is bus error control. Okay, so if you remember back, the bus error control is denoted by this pin. Okay, this BERR here is over here, bus error control. So what does this bus error control do? So it enables the 68K to recover from errors within a memory system. Pin in this group is BERR, example of a bus error. Okay, so what happened? This is just a pin to denote that currently there's something wrong. So example of that something wrong, yeah, when the microprocessor wait peripheral signal too long. So whenever you see, if you look back at the read and write cycle, there's always this acknowledgement to tell that 68K that the peripheral acknowledge that the data is being sent, or the data is being read, or the data is being write, or whatever. But whenever that detect is not being detected, this BERR will be put to high. So meaning that whenever there's something wrong, this will get high, this pin will get high. That is example whenever the microprocessor wait peripheral signal too long. And then type of a bus error is whenever parity error happens. Parity is basically a problem with the memory. Okay, what happened during this type of what happened when the BER is put to high? Okay, when BERR is put to high, first the microprocessor, your 68K, will discard all of the data. Okay, and then all of the address and data bus will be put in tri-state, meaning that it will be put in high impedance state. So you can imagine it to be in a reset state lah. Okay, in a reset state, and bus control pin will be disabled. So all of the bus control pin will be disabled if this is active. Okay, and then we're going to look at bus arbitration control pin. So what is bus arbitration control pin? Allows more than one CPU to share the address and data bus. So this is basically a control pin whenever you want to connect your 68K with another 68K, by at the same time both of the CPU, both of your 68K is sharing the address and data bus together, the same address and data bus. So this topic is a bit complex, so will not be covered in this course, but it's just for you to know that it exists, this type of pin, bus arbitration control pin. So there are 3 pins in this group. First is your bus request pin will be given 0 by the external device that want to use the bus. So this is the input. So whenever you have like example, yeah, your 68K connected together, and both of this is sharing the same bus. Okay, both of this is sharing the same bus. So bus request, okay, BR, okay, BR is a pin signal to tell that, okay, this is your 68K. Sorry, I'm bad because I'm using my mouse to write. The bus request is put to high whenever other microprocessor, okay, or external device want to use a bus, okay. So because this is being shared, you cannot have two CPU sharing the same bus at once. So if one of the CPU want to use the bus, it must tell the other that it want to use the bus, so the other CPU must stop from using the bus or put its pin on a high impedance state. Okay, so this is the function of your this bus request pin, yeah. And then you have this bus grant pin. Okay, bus grant pin will be given 0 by the microprocessor to signal the microprocessor to receive input BR. So bus request pin just now, if you can see, goes from the requesting CPU to the other CPU. Bus grant pin is the opposite. Is to tell that this requesting CPU that you can use this bus. Okay, so just to acknowledge that, okay, this 68K is trying to access the bus. Okay, let's say I name this CPU A, CPU B, for clarification purposes. Let's say the A want a request from B, so, and then B have to acknowledge. So the way that B acknowledge is by using this PG pin. Okay, so basically telling A, okay, now A, I have grant you to use the bus. Okay. Okay, now because your CPU B have already tell A to use the bus, next you must have some sort of acknowledgement. So that is where BEKC, okay, BEKC comes in. So BEKC is trying to tell back CPU B that I have acknowledged that I am using the bus. Okay, so B have already granted A to use the bus, so A have to acknowledge back to B that it received the command, it received the acknowledgement, and it will take over the bus. So now the bus is connected to A instead of B. So this is what special purpose pins do. Okay, next we're going to look at your special purpose pins. Okay, this is special purpose pin that denoted by F0 here. Okay, because previously I've mentioned F0 to FC2, functional pin. I said the functional pin, FC0 to FC2. Actually, this is what we call as a function code pin, function code output. So function code output, what does it do? Is just to indicate the current internal processing state of the 68K, what type of cycle it is currently executing. So this is the purpose of the pin actually, and there's nothing special about it. So these 3 pins is used to denote what is the cycle type or what is currently being executed on the 68K. If I'm not sure whether this has been covered or not, in your 68K you have your user data and you have your user space and you have your supervisor space. Okay, so in your user space you have your user data in your user program. In your supervisor space you have your supervisor data in your supervisor program. So depending on the state of the pin, okay, this pin, if you remember back, if I'm not mistaken, is a unidirectional pin, because to tell, yeah, okay, it's a unidirectional pin, FC2 to FC0 to FC2, is to tell your external peripheral the state of your 68K, whether it is currently executing a user data or user program, or it is currently executing a supervisor data or supervisor program, or it is currently acknowledging that interrupt has been done on your 68K. So that is the function of your FC0 to FC2. So for example, if you have your FC0 at 0, meaning that you have your 68K here, okay. If, okay, this is connected to, try to, okay, sorry about that, because I'm not good at drawing because I'm using mouse currently, so pardon me. Let's say your 68K, you have your 68K here. Okay, there's 3 pin, FC0, FC1, FC2, 0, 1, 2. So let's say this is currently 101. So what does being denoted by this 101? If you can see here, 101 will denote that the 68K is currently in a supervisor mode. It's reading a supervisor data. Okay, so that is just what your functional code pin do. That's all. There's nothing special about it. And then other type of pins, we have your peripheral control pins, where it permit your 68K to control peripheral. Pin in this group are enable. So enable is for your 68K to generate a triggering signal to an external peripheral. Okay, we have the valid memory address to acknowledge 68K that will still acquire peripheral 68K, and data transferring must be synchronous with a signal. This is to tell the peripheral the data transfer between your peripheral and your 68K must be synchronous with the enable signal, with the enable clock signal. And lastly, we have the valid peripheral address. This become low when 68K is synchronous with the enable and cause the data transferring to be occur. So this is peripheral control pin. Okay, nothing much about it. And lastly, we have this interrupt control pin. So what is interrupt? Enable a peripheral to request attention and permit the CPU to identify the source of interrupt. Pin in this group are IPL0, IPL1 and IPL2. So we have, for 68K, we have 3 interrupt. So basically, whenever you have your 68K, okay, connected to other peripheral, so let's say this is whatever peripheral you have, I denote this by P. Sometimes you want your 68K to stop doing something whenever there's something happening with whatever it is with the peripheral. Okay, so how are you going to do that? Basically you can use this interrupt. So interrupt is pretty much straightforward, like what the name implies, is for the peripheral to interrupt whatever 68K is doing and to attend the peripheral. Okay, so that is what interrupt do. Okay, what interrupt does. So there's a lot of usage for interrupt actually. For example, one application that I can think of is as a counter. Okay, as a counter. For example, if I don't know whether you're familiar with this. Sometimes, okay, you use an encoder to measure the speed of a motor. Okay, let's say you have a motor over here, right? Okay, this is a very widely used case of interrupt. Okay, this is actually connected to an encoder. Okay, encoder. So this is the encoder. You want to calculate the speed of the motor here. You want to calculate the speed of the motor here, denoted by omega, for example. And then you have your encoder here. So if you are familiar with encoder, the output of the encoder is in 0 and 1, 0, 0. Is a pulse, is a train of pulse actually. 1, 0, 1, 0. So you want, because the position and the speed of the motor is highly depending on the speed of the pulse here, you want your microprocessor 68K to be able to count this pulse. So one way of achieving this is by using interrupt. So this pulse here will be connected to interrupt. Okay, interrupt. So whenever there's a pulse, it will interrupt your 68K and will count the pulse. So this is one application of interrupt that is normally being used. Okay, so I guess that's all for today. Pretty short lecture from me. So if we will continue with the next chapter probably after your holiday. So I wish you happy holiday and don't forget to take my quiz. Okay, thank you very much guys.